Hello everyone. We'll be discussing now the concept of strain energy, and this is a very important concept to be learned in elasticity. So let's proceed. What some background about it, and then we'll begin doing what we want to do. Okay, let me just choose a right color. Okay. And this, as we have learned, in the last part, we have learned how to formulate the problem of elasticity, boundary value problem of elasticity, using either the stress formulation, traction formulation, or the displacement formulation. And in reality, as I've said, the problems would be mixed in the sense they would require you both, a mixture of both. So before we move on to actually learn how to solve the problem which we have formulated, this is an interim chapter and this is the right place to discuss for the reasons you will see over here. Okay, so let's see the motivation of this. So when you have a boundary traction and forces which will act on an elastic solid, there will be work done by these forces which is stored in the form of strain energy in the solid. Okay, so every solid which is strained will have strain energy with it. A very easy demonstration about this is that you hold a piece of paper in your hand and then try to tear it. Okay, when you try to tear it, you will hear a sound. Okay, that sound is not coming from your hands, it's coming from the part where the tearing is happening in the paper. And we can say that this is the strain energy which is being released, at least partly, which has converted to sound energy and we are able to listen to it. So strain energy was converted at least partly into the sound energy and we are able to see it. So that's where this sort of qualitative proof that strain energy is real, it's not fictional, comes out. Okay, and let's see what this would mean. Okay, so let's first discuss what the strain energy should be. So you must already be aware about the first law of thermodynamics. Okay, for a system, the change in the work done plus the heat exchanged is equal to the change in the internal energy plus the change in the kinetic energy of the system. Okay, so you may already be aware the difference between internal energy and kinetic energy. So kinetic energy of the system is like the overall half into m into v square for this the whole mass of this system. On the other hand, internal energy is practically, say, the velocity of the atoms, okay, spinning of atoms, or even the nuclear, like electronic spin, electrons when they sort of orbital motion, they have a energy, and many such other internal things. So this is all what the internal energy of a system is. And work done is because of the external agents only, and heat exchange is what the system exchanges, either give or take from or to the surroundings. Okay, so the work done by the forces which you apply, or either the surface force or the body force on an elastic solid, is stored inside the body in the form of strain energy. So that's where we are coming from. Obviously, you will have to think about what terms are zero in this for this statement to be made. Okay, I'll write the statement. The work done by the surface and body forces on an elastic solid is stored inside the body Okay, so using the first law, obviously the work done is already accounted for over here. Now you have to think of in what form will the strain energy manifest itself. Will it be due to the heat exchanged? Will it be due to internal energy? Will it be due to the kinetic energy? I think the answer is straightforward, but you should be able to think about it. Okay, so we have to consider only an elastic solid in which the stored energy is recoverable. What it means is that once you apply external forces, surface or body, there is deformation, there is strain, and then there is strain energy, and as you remove it, the strain energy will be coming back to zero. So whatever work you have done gets converted to strain energy, and once you remove that, the system will do work so that the energy which has been stored is completely used. Okay, so the energy comes back to zero. Now first let's take a case of a uniaxial deformation with no body force. Okay, let's do that. So we have a deformation under uniaxial. Dx, dy, dz. Okay, so this is the x, y, and z. So there is no body force that is given. So the cubical element has dimensions as you see dx, dy, dz, and it is the under the action of a uniform normal stress sigma in the x direction. So that is already shown. Now during this deformation process, we assume that the stress increases something like this. This sigma increases, okay, from 0 to this value sigma. Let's not assume a linear straight way, but let's assume that it increases from 0 to sigma during this deformation. Quasi-statically. Okay, so the reason this is done is that the body should be in equilibrium at all times. Okay, remember this quasi-static increase is not something very new to us. Remember, if you were defining, say, the potential, either the gravitational or electrostatic potential, the concept was that you would bring one unit of mass from infinity to a radius r from this, and that's how you would uh, define a gravitational potential at a distance r from this capital M. Similarly, an electrostatic potential is to bring this 1 unit charge, the work required to bring this 1 unit charge from infinity to this distance r from this charge q. Okay, now this work done, this bringing 1 unit charge or one unit mass from infinity to this distance r is done quasi statically. Okay, we don't suddenly bring this, or it's not the particle or the charge at no point is accelerating. So that is one requirement which we had seen before in our earlier school days, and that's what we exactly want to do. The concept is that if it was in equilibrium over here, in the next stage it should be in equilibrium, in the next stage it should be equilibrium, in the next stage it should be equilibrium, and so on, and even finally it is in equilibrium. So it is in equilibrium with respect to the previous stage. That's the meaning of quasi-static increase. So that's what we want to achieve, and it increases from 0 to sigma x. Okay, this is the final value for this, and the inertia, the technical language is inertia effects can be ignored. No acceleration at any stage. Okay, now in this case, the strain energy stored in the body according to the first law. So I think by this time you have already known the answer, that the strain energy manifests itself in this particular term. Okay, because the system is not having velocity as a whole, the center of mass of the system is not having a velocity at any stage, and there is no heat exchange from the system to the surrounding. So the strain energy manifests itself in this term delta U, which is the strain energy, then internal energy in the first law of thermodynamics. Okay, so the strain energy stored is equal to the net work done on the element, and that can be given. How is the net work done calculated? You calculate at any given stage the force sigma, and how would this force come out to be? You would multiply by dy dz. Okay, and then you have to multiply it by d into u plus dou u by dou x into dx. So remember, the work done is equal to F dot du. Okay, now in a case where both force and the infinitesimal displacement is in the same direction, you can just write it as F du. Okay, and this is how this term is written over here. So this particular face is what we are looking at. Okay, assuming that the other face has not moved. I mean, so we are taking this particular phase as the reference phase, and we are trying to see how much this phase has moved ahead. So that has moved ahead by u plus dou u by dou x into dx, and obviously it is written using the Taylor series expansion as we have done before. If this phase has moved by the distance u, how much has this phase moved? That would be u plus dou u by dou x, ignoring the higher order terms. So we have done that before several times. Okay, so this is how the work done is written, and all that work done is in terms of the stored in the form of strain energy, and you have to write now for the other phase where it is going from 0 to sigma x, sigma dy by dz into du. Okay, because this particular, just like sigma is causing a deformation in this particular phase, this sigma, which is minus sigma, is causing a deformation in the other phase, and that phase is u. Okay, so that's why you are writing as du. The displacement is u of this phase. Okay, I hope you can see why the negative sign has come up. Now you can write it as 0 to sigma x. This would come out to be sigma dy dz d of dou u by dou x into dx. Okay. Yes. Just du and du will cancel on both sides, so you would have this. Now I can write this as 0 to sigma x sigma into d dou u by dou x into dx dy dz. Now if you use the Hooke's law and strain displacement relation, let's see what strain displacement relation is. Ex is equal to dou u by dou x. Okay, we know this. But Ex is also equal to sigma x by E. In a one dimensional case, you would only have this as your Hooke's law. There would, because the other terms are 0. Okay. Now, what you can do is you can now substitute this over here and write it as 0 to sigma x sigma into d by dou u by dou x can be written as Ex, right? Dx dy dz, and Ex can be written as sigma x. E can be taken out because it's a constant. Dx dy dz. Okay. This implies that du is equal to sigma x whole square by 2e dx dy dz. Okay, basically you are only doing this, only doing this. Okay, the integration is in terms of sigma. Okay. Yes, sorry, I should write it as okay, sigma x is the final value, so I should actually write it as d sigma over here. Okay, this is the final value. At any instant, if I have to write it, I will write it as Ex is equal to sigma by E at any instant. So that's why this has happened, and this would be sigma x square by 2e dx dy dz. Now the strain energy density per unit volume will be written by du by dx dy dz. Okay, so this is how we are defining this. Let me just put it this way. This is the strain energy density, and we can write now u is equal to sigma x square by 2e, or using Hooke's law, look at this one, you can write it as ex square by 2 or half into sigma x into ex. Remember, this is the final stress and this is the final strain. Obviously both of them are from 0 quasi-statically. That was an assumption over here. Okay. So if we want to interpret this, you can say that if you draw a graph between stress and strain, and in linear elasticity the relationship between stress and strain is linear, that's what you have assumed over here. Okay, the relationship between stress and strain is linear, and you would have this sort of a relationship. So if your final value of sigma x happens over here, Ex happens over here, U is this shaded area under this curve, that is U. Okay, now let's briefly go through a similar uniform shear stress. We have taken a uniform tensile stress before. Let's consider a uniform shear stress. Let me first draw an element. So this is the element, undeformed. Okay, we are only doing a two-dimensional one for this, just because it's easy to draw, no other reason. So you have the original dimension as dx and dy, this rectangular element, and this particular length we have shown in the geometrical interpretation of strain as dou v by dou x into dx. Let me check that. Yes, so this has been found out as dou v by dou x into dx in the geometrical interpretation of strain. Similarly, this has been found out to be dou u by dou y into dy. If you are not sure how this has come up, please go and check that, and you should be convinced how dou v by dou x into dx and dou u by dou y into dy is these lengths. The shear stresses are shown tau xy and tau yx. Okay, so this is the uniform shear stress which we have, and we'll choose a similar understanding that it goes from 0 to tau xy or tau yx quasi statically. Okay, that means very slowly. Okay, so you would have to calculate the work done. Okay, and then you would have uh, the strain energy coming up. So du in this case would be equal to half into tau xy. Okay, so there is a z dimension, but that is hidden. Dz is there but hidden. We didn't show that. So what would be the force? Tau xy is acting on the face, which is dy into dz. Okay, and then the other one would be dou v by dou x into dx. So this comes after your integration, and then on the other face, which is this face, you write it as a half into tau yx dx into dz into dou u by dou y into dy. Please do not proceed ahead if you have any doubt how this is written. Actually write it like we have done in the previous case. This way you will understand whether you can actually write the strain energy density and the work done correctly. So this is the answer, but before this there is one step which you should do. Okay, after this you should have half of tau xy into dou u by dou y plus dou v by dou x into dx dy dz. Okay, so this is the reason this has happened is because tau xy is the same as tau yx. So this one you can replace by tau xy directly. Okay. Now the strain energy density, just like in the previous case, can be written as half tau xy dou u by dou y plus dou v by dou x. Okay, and that we can write as tau xy into half into gamma xy. Remember, this is the engineering shear strain, and that's why you don't have a factor of half. Okay, and this, just using the Hooke's law, can be written as tau xy square by 2 mu equal to mu gamma xy whole square by 2. One of the things which you should notice by looking at this, so this was, if you remember, what is for pure uniform tension, the strain energy came out to be half into sigma x square by 2e equal to e epsilon x square by 2, and in uniform shear this came out to be half into tau xy square by mu equal to half into mu gamma xy square. Both these we have derived, and we can make this note that the strain energy is not a linear function of stresses or strains. You can see there is a square in both stresses and strains when you write the strain energy density, either in tension or in shear. Okay, this implies that the principle of superposition cannot be applied on strain energy density. Okay, what it means that if we have tension and shear both, okay, we cannot do something like this, okay, and write out the strain energy of 1, strain energy of 2, and we cannot do this due to principle of superposition. We cannot do this, okay, because it's not linear in either stress or strain. Okay, however, I am still saying that if we have all the stresses acting, the strain energy density can be written as sigma x ex plus sigma y ey plus sigma z ez plus tau xy gamma xy plus tau yz gamma yz plus tau zx gamma zx. This can be written as, I'll show this later on. Okay, I will show this later on, then I'll remove this question mark. But the important point right now is, despite the fact principle of superposition is not valid, I am somehow still writing all the terms by just adding them. Why can I do that? Okay, for a multi-dimensional state of stress, So for a multi-dimensional state of stress, we are still able to write it. The reason is because of conservation of energy. Let me demonstrate what I mean by that. So if you have say these two states of sigma x and sigma y, okay, both going from 0 to sigma x and sigma y separately. The logic is this: first take this solid, okay, apply a sigma x like you did before, and you will have a certain energy u1 stored into it. Then take this deformed solid and now only apply sigma y. You will have a strain energy due to this, which will again be added. So finally you will have u1 plus u2, and then you keep on applying, say now, a shear force, okay, tau xy, tau yx. This time you will have u1 plus u2 plus u3. So take an undeformed solid, apply this, certain strain energy will be stored in the solid, okay. Now keep that sigma x over there, don't remove sigma x. Sigma x is still there, it's now constant. Now you slowly apply sigma y from 0 to sigma y slowly. Then you will have an additional strain energy stored over and above what was already stored, and so on. So that is how you keep on going, and each element will now be contributing and adding to it. Is it the same as principle of superposition? The answer is no. Yes, mathematically it looks the same, but it is not the same thing. The reason for writing this is due to the conservation of energy. The strain energy is stored and retained because you are not removing sigma x. And then the next set of loading sigma y is acting, and so on. Okay. So let's see how this can be written. So let's see, half u is equal to half sigma ij e ij. That can be written as half sigma I1 e I1 plus sigma I2 e I2 plus sigma I3 e I3. Now each of these terms can be written as half into u is equal to half into sigma 11 e11 plus sigma 21 e21 plus sigma 31 e31 plus, now this term, sigma 22 e22 plus sigma, sorry, sigma 12 e12 plus sigma 22 e22 plus sigma 32 e32. Now the third term would be sigma 13 e13 plus sigma 23 e23 plus sigma 33 e33. Okay. As you already know that this term and this term is the same, this term and this term is the same, and this term and this term is the same. Okay, so we can write it as half into sigma 11 e11 plus sigma 22 e22 plus sigma 33 e33 plus 2 times of sigma 12 e12 plus 2 times of sigma 13 e13 plus 2 times of sigma 23 e23. Okay, and this would be half into sigma 11 plus e11 plus sigma 22 e22 plus sigma 33 e33 plus, now this 2 times of e12, as you know, I will just write it now in the xy system. So this will be sigma x ex plus sigma y ey plus sigma z ez, and this 2 times can be written as sigma xy gamma xy, okay, because 2 times of exy is equal to gamma xy. Similarly, this can be written as, this can be written as sigma xz gamma xz plus sigma yz gamma yz. Okay, and this is this expression over here. Okay, So you can see how in the shorthand notation, the strain energy density for a multi-dimensional state of stress when all components are present can be written as half sigma ij Eij. Okay. Now let's take up a question over here. So we have developed preceding results for the case with no body forces. Remember we had excluded the body forces. We can show that results are same if body forces are included and stresses are allowed to vary continuously. So this is, I think, the first question in your textbook for this chapter. We want to, I'll repeat the question. So do you have the uniaxial deformation which was shown? Okay. And let me just show that over here again. Okay, similarly this will be u and this will be u plus dou u by dou x into dx. Okay, so this is there. Now we have to find the strain energy for this case in which the stress will vary continuously as a function of x. Okay, stress will vary within this as a function of x, and we have to include the body forces. Obviously we will consider the body force only in the x direction because we are only concerned with the x direction for now. Okay, so let's see. You want to again write the work done. So this time let's take up first of all the right face. Okay, the right face should have this as sigma plus dou sigma by dou x into dx. So if it is sigma x on this face, since it is continuously varying, it will be sigma plus dou sigma by dou x into dx. This is just the Taylor series expansion again, writing the stress on the right face with respect to the stress on the left face, just like you were writing the displacement of this right face with respect to the displacement on the left face. Okay, so let's take the right face first. Work done by the forces on the right face, that would be sigma plus dou u by dou x into dx multiplied by area which is dy dz and the displacement which is d of u plus dou u by dou x into dx. Okay, now we have to write the work done by the force on the left face, which is this. So this will be 0 to sigma x. Minus sign is there because it acts, force acts in the other direction. Sigma into dy by dz, this is the force and the displacement is u. Okay, Remember, there is also body force which will do work, so there will be a contribution due to that, and that would be Fx into body force density. Okay, Fx is the body force density, so we will multiply it by the volume, which is dx, dy, dz. Now this becomes a force, and we must multiply this with the displacement of this by 2. Okay. Now there are many ways to see this, but let's see what should be the displacement of this. Okay, so we remember we have to write this du term. Now you assume that the body force is acting on the center of mass. Okay, which is not a very bad assumption to take. Assume that body force acts acts on the center of mass. Okay, so what is the displacement of the center of mass? Now what we do is the displacement of this face is u. Okay, the displacement of this face is u plus dou u by dou x into dx. Okay, what would be the center of mass, displacement of the center of mass? That would be u plus dou u by dou x into dx by 2. Okay, so that's what we do over here. We will write it as u plus dou u by dou x into dx by 2. Okay, now let's see what this gives us. Okay, 0 to sigma x sigma dy dz d of u plus dou u by dou x into dx plus dou u by dou x into dx dy dz d of u plus dou u by dou x into dx minus 0 to sigma x sigma dy dz du. 0 to sigma x fx dx dy dz d of u. Okay, plus 0 to sigma x fx dx dy dz d of dou u by dou x into dx by 2. Okay, few more terms to go. 0 to sigma x sigma dy dz du plus 0 to sigma x sigma dy dz d of dou u by dou x into dx plus dou u by dou x into dx dy dz du plus dou u by dou x dx dy dz d times of dou u by dou x into dx. Okay, minus 0 to sigma x sigma into dy dz du plus 0 to sigma x fx dx dy dz du plus 0 to sigma x fx dx dy dz to t into du by du to x dx by 2. Okay, anything which we can cut out? Definitely there's only one minus sign. Let's make the best use of it. Okay, it seems this and this can go, and I think I've forgotten the integral sign, which is 0 to sigma x. Okay, now this I want to write it simply as what were we doing? We were trying to find du. Okay, that's what we should always write in a lengthy derivation, otherwise we forget. Okay, let's see the higher order terms and perhaps we can ignore them. Okay, so can we write this as sigma into 0 to sigma x d of dou u by dou x into dx, dou u by dou x, sorry. Yes, dou u by dou x into dx dy dz plus dou sigma by dou x plus fx into dx du, sorry, into du dx dy dz. How can we do that? So clearly we are just taking this term okay, and we are definitely taking one more term over here. Which one? I think I have done some mistake somewhere. I think the mistake is over here. This is actually d sigma by dx. Okay, so this should be d sigma by dx, and this should be again, so this should be 0 to sigma x d sigma okay. So it seems we have taken clearly this term, we have taken this term, okay, and we have taken, have we taken this term as well? Should be some more terms which are there. For example, du dz du, okay. Okay, so we should have one more term. Let's see, these two terms are sorted, it seems, at least, because these two terms are this term. Now I think there should be a sigma somewhere, just not able to get hold of this. This is a good exercise. So 0 to sigma x plus Sigma. Let's check each term. 0 to sigma dxy. Zero is dy dz d plus d sigma. Okay. Now sigma dy dz d of sigma dy dz du plus sigma dy dz, okay, plus 2 sigma. There should be one more term of d sigma. This should be that term of d sigma, I'm guessing. And then the normal sigmas come along. So sigma, how many terms should be there? There should be a total of 4 terms before the minus 1, 2, 3, 4. Okay. So once this is done, I think we should now be able to write this as this one. Okay. And this can be written as 0 to sigma x sigma into dou u by dou x by into dx dy dz. Why will that happen? Because this, if you recall, is the equilibrium equation in x direction. Okay, and that is equal to 0. So you are left out only with the first term, and this would imply this is equal to 0 to sigma x sigma into sigma. So this is actually ex. Okay. Or this can be written as 0 to sigma x d by sigma by e. We're using the Hooke's law, dx dy dz. What we have done is we have ignored the higher order terms in this part, okay, and only written the remaining terms. So you have to figure out which are the higher order terms and why can they be ignored. Okay, anytime you see a 2-time derivative, that's what has been ignored. Okay. And it is very easy for you to apply the chain rule. For example, I think I should just write some hint over here. Hint. You have d of dou u by dou x into dx. Do check this derivation once for some possible typo, but so it will be d by dou u by dx into dx plus dou u by dou x into dx square. Okay, so definitely this particular term can be ignored and this can be retained. So this will be dx into dou u by dou x, and hence you see this particular term is appearing over here. Okay, so you have found out that the strain energy density, even in the presence of a body force where the stress is uniformly varying along the x dimension, can be found out in this form. Okay, just you do this integration and you find dx dy dz, or the strain energy density is sigma x square by 2e. So this is same as before, and hence if you extrapolate the same thing, you will get U equal to half sigma ij Eij using the same conservation of energy arguments even in the presence of a body force. So that is how you can show that this result is valid even in the presence of the body forces. Okay, so if you want to now write the total strain energy stored in the body, all you have to do is multiply the strain energy density with the volume. Okay, so let's move ahead and write the Hooke's law. Uh, so if U is equal to half sigma ij Eij, we want to use the Hooke's law to eliminate stresses. Basically, we want to write strain energy density in terms of the strains only. Now I am showing this with a vector sign just to tell you that it's a bold symbol. Okay, it's not actually a vector, it is just a bold symbol to tell you that it's in terms of the tensor, strain tensor. Okay, so remember what the Hooke's law was. Sigma ij would be equal to sigma ij is equal to half. So this would be half sigma ij is lambda ekk delta ij plus 2 mu eij. Okay. Okay. So we want to now write this as lambda. Let me just call it ekk delta ij eij plus half and half is out. That would be mu eij eij. Okay, this can be written as half into lambda ekk into ejj, because for non-zero values I will have to be equal to j, and this is written as mu into eij eij. Okay, so this in terms of strain can be written like this. Similarly, one can write the, so let me first expand this and write this as lambda into E11 plus E22 plus E33 whole square. So that will be Ex plus Ey plus Ez whole square plus mu into, there will be a total of 9 terms, but because of the symmetry of those terms, we should be able to write Ex square Ey square Ez square plus half into mu xy square plus half into mu yz square plus half into mu zx square. Okay, so you should definitely expand this term and see that you can write it in this form, and you have to write it in exactly this form. Okay, there is a reason for this which will become clear in a minute or two. Similarly, what you do now is try to write the strain energy density in terms of stresses only. That way you will have to eliminate the strains from this. So for this you recall the inverse of the Hooke's law, where Eij was written in terms of the stresses. What was that? This was half into sigma ij 1 plus nu by E sigma ij minus nu by E sigma kk delta ij. Okay, so this would simplify. Let's see what it would simplify to. This should become half of 1 plus nu by E sigma ij minus half of nu by E sigma kk sigma ij delta ij. That would make it 1 plus nu by 2E. What is sigma ij? Sigma ij, you can write it in the expanded form. Let me just write it here for now. Sigma ij minus nu by 2E sigma kk into sigma jj, because for non-zero values I will have to be equal to j. Write this in the expanded form. It would become 1 plus nu sigma x whole square plus sigma y whole square plus sigma z whole square plus 2 times of tau xy whole square plus 2 times of tau yz whole square plus 2 times of tau zx whole square minus nu by 2e into sigma x plus sigma y plus sigma z whole square. Okay, sigma 1 1 plus sigma 2 2 plus sigma 3 3 twice. So that's what this will become. Okay, now please clearly observe these two relations: strain energy density in terms of strain and strain energy density in terms of stresses. Okay, one of the things which you would develop, which you would observe, is that the strain energy is a positive definite quadratic form. Okay, you see this relation, for example, it is a term which is square, so it can only be 0 or positive, and then this term is also made up of lots of squares, so this can also be 0 and positive, and there is a positive sign. So we can clearly say that strain energy density is a positive definite quantity over here. Okay, now can you make a similar observation over here? The answer to this is yes, but please make this, it's a homework for you. Okay, this will ensure that you have understood the philosophy behind doing this. So in either case, obviously u will be greater than equal to 0, and u will be equal to 0 if sigma ij or eij is equal to 0. Okay, it is very clear that if there is no deformation, then there are no stresses, and if there are no stresses and no deformation, there cannot be a strain energy density. So one of the things which I have to mention without proof is that u greater than equal to 0 has been shown for isotropic solid, obviously linear elastic isotropic solid only. I am stating this without proof that this is valid for linear elastic and isotropic solid as well. Okay, let's just say that proof cannot be done in this particular course. It's very simple to do, but it should not be perhaps done over here. So that's the first thing. It should be stated without proof. The strain energy density is 0 even for an isotropic solid, say a composite for that matter. Okay, now if you want to differentiate some of these relations, so let's see, if you have say the strain energy for a uniaxial system, for example, for a uniaxial deformation, Okay, so you have u is equal to sigma x. We have already done this, sigma x whole square by 2e, and we by this time we also know that this relationship is valid with or without body force. Okay, so if you now do a dou u by dou e in terms of dou ex, that would be dou by dou ex. It is equal to ex whole square by 2 ex is equal to sigma x. Okay, and so the stress could have been found by partially differentiating the strain energy density written in terms of strain with respect to the strain. Similarly, if you partially differentiate the strain energy density written in terms of stress in terms of the stress, that would be dou by dou sigma x. This would be sigma x square by 2e is equal to sigma x by e is equal to ex. You will end up with strain. Okay. So we want to now generally write it. Okay. We want to claim that the strain, so this is a question in fact from your textbook, to prove that sigma ij is equal to dou u by dou eij. Okay, so this is a more general form. Obviously this was for a uniaxial deformation, and this is for a more general case. So let's try to attempt this. Obviously, to be able to prove this, we have to write the strain energy density in terms of this strain only. So let's do that. So we know, so this is a solution. We know that u is equal to half sigma ij eij, and we have to eliminate the strains, and that we have already done, which comes out to be ejj ekk plus mu eij eij. Okay, now you want to take the RHS of this, that means dou u by dou eij. You want to write it as dou by dou eij half lambda ejj mu eij eij. Let's take it one step at a time. So let's take it. Okay, lambda by 2 dou ejj by dou eij into ekk plus ekk by dou ij will be equal to ejj. Okay, let me do something over here so that it becomes less confusing to work with. In fact, let me start from over here because the i's and j's may confuse us. So let me do it in another way. Perhaps you may be knowing some other way to do it, but I'll just go by the method which has always worked, which is using the fundamentals. So let's see, you want to show that tau u eij is equal to sigma ij. So let's start with the uh, right hand side, and eventually we'll prove that it is equal to the left hand side. Okay, so that should be dou by dou eij. U is half into lambda ekk delta ij plus 2 mu eij. This is half into lambda ekk delta ij, because delta eij will get differentiated, and then in the second part of it we will have a 2 mu eij, because the other strain would have gone. Now then the second part comes in, half into eij dou by dou eij lambda ekk delta ij plus 2 mu eij. Okay, so this is just the chain rule which has been applied over here. Okay, so essentially you first differentiated this, and then in the second case you differentiated this. So it's just a simple chain rule which has been applied over here. Okay, that's what dou u by dou eij is. So let's now take the first let's take up this one. Okay, since it's somewhat complicated, and I'll use a different ink, not a red one. So let's consider this tau of tau eij lambda ekk delta ij plus 2 mu eij. Okay, now we want to apply we want to do this differentiation, so that would be dou by dou eij lambda ekk delta ij plus dou by dou eij 2 mu eij. Let's see what this comes up. So we have to apply, as you know, the chain rule of differentiation. So let's do that. Once lambda comes out, definitely not an issue. This can be written as delta ki delta kj and delta ij. I'll come to it why. And this comes out to be 2 mu. Let's see this. So lambda coming out is not a problem. Okay, now if you want to apply the chain rule, so lambda of this first term, you would have dou ekk by dou eij delta ij plus ekk by delta ij by dou eij. So this is not a problem because this quantity is either a 0 and 1. If you partially differentiate it, you will always get a 0. Okay, and when it comes to this particular quantity, this can be written as delta ki and delta kj, Reason is that if k is equal to, so for example, dou ekk by dou eij, this quantity is equal to 1 only for, say, cases like this. And so on, okay? Meaning dou EPQ by dou EJK is equal to 0 for all cases where EPQ is not equal to EJK. And hence this is a nice way to write all cases where this K is equal to I and K is equal to J. Both of them have to be true. That's how they are written like this. And that's how this term is written. Okay. Now let's continue with what we were doing. Okay, so this was some sort of a explanation. Now let's come back. Dou u by dou eij is equal to half into okay, sorry, there's a plus term, right, of eij, and then this thing in green should come up. It's lambda delta ki delta kj delta ij plus 2 mu. Okay, this can be written as half into lambda ekk delta ij plus 2 mu eij plus half into lambda ki, sorry, delta ki delta kj delta ij, sorry, and eij plus 2 mu eij. Okay, sorry, let me just reverse this. Let me write it as eij and delta ij. Now please focus all your attention to this particular term. For this to be a non-zero, I will have to be equal to k and I will have to be equal to k and j will have to be equal to k. So this would just become this. This would imply that you have half into lambda ekk delta ij plus 2 mu eij plus half into lambda ekk delta ij plus 2 mu eij. This implies that this is lambda ekk delta ij plus 2 mu eij. And this, if you know by the Hooke's law, is the stress, which is equal to LHS, hence proved. So you have proved in general that the sigma ij is equal to dou u by dou eij. We have just done this. Now it is your job to repeat this analysis. Please do this to prove that this is true. Okay, please don't ignore this, and as I always say, this is the only way you will understand whether what you have learned before is actually correct. Okay, Again, we have proven this to be for this relation to be true for linear elastic isotropic solid, but stating without proof that this is valid, also valid without proof for anisotropic, okay, or even non-linear linear elastic anisotropic or even non-linear solids. Okay, I am not including the proof over here because perhaps for many of you the proof is simple enough if you have done continuum mechanics as a course. If you come from the first law of thermodynamics, then this is very easy to prove. But in this particular course, we'll just state it without proof that this relation is only valid even for a non-linear elastic material, hyperelastic material, or whatever be the case. Okay. Okay. Now, so using this, we'll also be proving some other properties. This is also again a question from our book, which is dou sigma ij by dou EKL is equal to dou sigma KL by dou EIJ, and dou EIJ is dou EIJ by dou sigma KL equal to dou EKL by dou sigma IJ. Okay, so we'll try to prove one of it. Let's see if we can. Okay, so we know that sigma ij is equal to dou u by dou eij. We have shown that. Okay, now let's pick up this term. So dou sigma ij dou EKL is equal to dou 2u by dou EKL dou EIJ. So this is the left hand side. Okay, now take out the right hand side separately. Okay, so we can write sigma KL is equal to dou u by dou EKL. Okay, just like we can write this in this form just by simple interchange. I can be written as K and J can be written L. Now the right hand side of what we intend to prove can be written as dou sigma KL by dou EIJ is equal to dou 2u by dou EKL dou EIJ. Sorry, this should be written as dou EIJ dou EKL. This is dou EKL dou EIJ. Now LHS is equal to RHS because the order of differentiation does not matter. Whether you differentiate first with respect to EIJ, then with respect to EKL, or first with respect to EKL, then with respect to AIJ will make no difference. Hence, the left hand side is equal to our right hand side. Similarly, you must repeat this and prove this particular property as well. Okay, this is left out as an exercise for you to confirm whether your understanding is clear. Now, using these two properties, we will prove another property of elasticity tensor. Remember, we had already shown that Cijkl is equal toCijkl, and it is equal to alsoCijlk. Okay, both these things we were able to prove due to the symmetry of the stress and strain tensor. A third property which will be shown now or proven now in front of you is this one. Okay. Now we want to prove this. Okay, this is also again a question from the book. Prove this property. Okay, so for this we proceed again, and this is obviously true for an anisotropic solid, nothing to do with elasticity. So we want a way to be able to prove this relationCijkl equal to Cklij. Let's see how we can do that. So let's start with the Hooke's law, which is sigma ij equal toCijkl ekl, and then use the other Hooke's law, which is Ckl equal to Cklij eij. So both of them are the representation of the same Hooke's law, just the indices have been changed. Now if you partially differentiate this one with respect to ekl, you will getCijkl. If we partially differentiate this one with respect to eij, we would get klij. The reason is thatCijkl would be a constant, so any partial derivative which comes as a result of the chain rule will actually be 0. Okay, so once this is done, now you have to look at this property. Dou sigma ij dou ekl equal to dou sigma kl by dou eij. Okay, so this would imply that Cijkl is equal to Cklij. Okay, so this is how we have proven this particular property. Now it is also said that you can make certain assumptions or simplifications over it. Remember the form which we had before, which was sigma I equal to Cij Ej, where sigma I would be sigma x, sigma y, sigma z, tau xy, tau yz, tau xz, and ei would be equal to ex, ey, ez, 2 exy, 2 eyz, 2 exz. Okay, this was, remember, a 6 by 6 system. So if you compare this one with this particular property, you can say that Cij will actually be equal to Cji, because say this one and this one gets interchanged. So same happens over here. This comes over here and this happens over here. Okay, so this would mean that there are only 21 independent constants. So there were 36 after the symmetry of stress and strain, and now there are 21 independent constants for a anisotropic elastic solid. How there would be 21? It's quite easy to see. So if you have 1, 2, 3, 4, 5, 6, and then you have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So we want to count the independent ones. So clearly this is the same as this one. So we'll count it only once. Okay. this one. Okay. Similarly, this all of them will be counted once. Now again symmetry calls this one. Now 3 and 1 plus the diagonal terms, because they don't have any reduction. So you will have how many? 1, 2, 3, 4, 5 plus 4 plus 3 plus 2 plus 1 plus 0. How many? 5 plus 4, 9, 9, 3, 12, 12 plus 3, 15 plus 6 diagonal. So you have 21 independent terms in this elasticity tensor for an anisotropic solid. Okay, so just like the strain and stress could be decomposed into two parts, one for volumetric, the other for distortion, which was the change in shape. One can write the strain energy density as UV plus UD, and UV can be written as half into sigma ij Eij. Remember, sigma ij tilde and Eij tilde is the volumetric stress and strain. Okay. So for an isotropic solid, you can write the stress in terms of strain. So that would be given as 1 by 6 sigma jj ekk. Okay, this diagonal terms only. And this would be, if you now write the Hooke's law for an isotropic solid, you can write it in this form. Okay, and this one should be able to write 2 nu by 6e sigma x plus sigma y plus sigma z whole square. Okay, I would request you to verify these forms. Okay, similarly the distortional part. Okay, how will you find the distortional part? Like again, take the total strain energy density, subtract the volumetric part of it, and then you should have a value. This comes out to be 1 by 12 nu sigma x minus sigma y whole square plus sigma y minus sigma z whole square plus sigma z minus sigma x whole square plus 6 times of okay. So this is again something which you should be able to verify. Please don't leave out this verification. These are important things not to be missed. Okay. So let us take up sort of one question over here. Let's see if we can do that. One of the first things which is said that, I mean, just like stress is used, principal values of stress is used in failure theories, which you may have seen before. There are also failure theories where strain energy density is used. Okay, and there are some other relationships which exist between the so-called octahedral strain energy density and the one which we have. So let's see if we want to do a question over there. Okay, so let's take up a question from our text, which is show that the distortional strain energy is related to the octahedral shear stress by the relation UD, which is the distortional strain energy, 3 by 2, 1 plus nu by E tau octahedral square. So 3/4 mu tau octahedral square. Okay. Okay. So we had to first, I had left out some part for you over here, which was this particular part, but since I have left for you to verify, I'll just take up at least one part of it, which is UD, which is relevant over here. Okay, so what I'll do is I'll write UD is equal to U minus UV, and that would mean that this is equal to 1 plus nu by 2E sigma ij minus nu by 2E sigma jj sigma kk minus 1 minus 2 nu 6E sigma jj sigma kk. Let's see, sigma jj sigma kk. Because this has been proven to be equal to UV in the part before, you should have verified it by now. And you can write this as 1/4 mu sigma ij minus 1/12 mu sigma jj sigma kk. Okay, so this should give you 1/12 mu sigma x minus sigma y whole square plus sigma y minus sigma z whole square plus sigma z minus sigma x whole square plus 6 into tau xy square plus tau yz square plus tau zx square. Okay, so UD has been shown as this one to you, and by its definition, the octahedral octahedral shear stress is given as 1/9 sigma x minus sigma y whole square plus sigma y minus sigma z whole square plus sigma z minus sigma x whole square plus 6 tau xy square plus 6 tau yz whole square plus 6 tau zx whole square. Okay, and this would imply that UD is actually equal to 1/12 mu 9 tau square. Okay, so as we have shown, there is a direct relationship between UD and tau oct, and you can like use other constants. For example, if you do not want to use, so 3/4 mu tau oct square, and then you can write it 3/2 1 plus nu by E tau oct square, either way. Okay, so you can do this question. So the distortion strain energy is related to the octahedral shear stress, which was earlier discussed. Now we come to a very important topic. Remember, I had already claimed in one of the lectures that linear elasticity has been flourishing for all this while because of two important reasons. One of them was the principle of superposition, and it's now time to study the second property. That is called uniqueness. the elasticity boundary value problem. So remember, we had formulated the boundary value problem and we have not actually gone into the solution part of it. But what we would want to claim over here is that for a linear elastic boundary value problem, which has been formulated in our earlier discussions, the solution is unique. Okay, that's what we want to prove. Now, like any formal proof of uniqueness, we always begin in the following way. We consider a general mixed boundary value problem in which traction are specified over St and displacements Su. Okay, so S, which is the total boundary of this solid, is made up of Su plus St, just like we had in the earlier case. Now, assume that there are two different solutions Remember, what was the solution of the boundary value problem? That for every point inside the solid, one must be able to find the strain, stress, and displacements given the body forces and the surface tractions or surface displacements, and the material properties were provided. So assume that there are two different solutions, sigma ij1, eij1, ui of 1, and sigma ij of 2, eij of 2, ui 2. To the same boundary value problem with identical body forces and boundary conditions. I mean, there would be no point if the boundary conditions are different. So we have identical boundary conditions. Now let's use a term called the difference solution. Okay, so imagine this was your boundary and there was a part of it which was St, the other part was Su, and any arbitrary point you would have two solutions, sigma ij1, eij1, ui of 1, and sigma ij of 2, eij of 2, and ui of 2. So the difference solution, meaning at the same point, the different solution can be written in this form. It's just a difference. I mean, it's also a tensor, as you can see, and it's just the difference between these two distinct, which were assumed solutions. Okay, and ui is equal to ui of 1 minus ui of 2. Okay, now the next claim is that we can write sigma ij comma j is equal to 0. Okay, how can we write it? So we can always write that at this point, the same point which is of interest, equilibrium holds. So C sigma ij1 comma j plus fi is equal to 0. Similarly, sigma ij comma j of 2 plus Fi is equal to 0, just because the body force is the same. Okay, now if you subtract the 2, you would get sigma ij comma j1 minus sigma ij comma j of 2 equal to 0. Now if you partially differentiate this equation with respect to xj, you would get sigma ij comma j is equal to sigma ij1 comma j minus sigma ij comma j 2, but this is equal to 0 because of this. Okay, hence sigma ij comma j is equal to 0. So you can similarly say that Ti of n is equal to sigma ij nj is equal to 0 on St, and Ui is equal to 0 on Su. The reason for this is that the boundary conditions on St and Su are the same. So let's see that. So imagine this dark part is St and the other part is Su. So at St, or first of all in general, Ti of n equal to sigma ij nj. Okay, now if you have the value Ti of n is equal to sigma ij1 nj, and then you have say 1, and then Ti of 2 n is equal to sigma ij2 nj. Okay, now if you subtract the 2, Ti of n of 1 minus Ti of n of 2, that would be Cij1 minus Cij2 nj. Okay, now this can be written as sigma ij, so that we can write it as sigma ij nj, and this can be written 0 because boundary tractions are identical, right? That was one of the conditions, and that's how this is true. Okay, by a similar logic, at boundary, if Ui of 1 is equal to, I don't know, x, then Ui of 2 will also have to be x. At the boundary, the displacement has to be the same, and this would imply that Ui1 minus Ui of 2 will be equal to 0, and Ui of 1 minus Ui of 2 is actually equal to Ui. Okay, so this implies that Ui is equal to 0. So that's where this and this are true. Okay, now we want to write the strain energy density. So let's see, strain two times of V u dV is equal to, or let me just say that u is equal to half sigma ij e ij. Okay, so this is at one point. Now if you want to write it for a small volume, say this dv volume, you can write u dv 2 times integral for this entire volume, for the entire solid, is equal to sigma ij eij dv. Okay, and then this term can be written as sigma ij minus ui comma j minus omega ij dv. Why? Because remember that every tensor can be written as a summation of symmetric and anti-symmetric part. This is something we had learned before. Okay, so this can be written, and this is all over the entire V. Sorry. Okay. Now this can be written as V into sigma ij ui comma j dv minus sigma ij u omega ij dv. Okay, this can be written as equal to sigma ij ui comma j dv. This term is a 0. Remember, you have a symmetric and an anti-symmetric. This product is equal to 0. So aij bij will be equal to 0. So the rotation is the anti-symmetric and stress is symmetric, and hence this quantity is equal to 0. So that's what we are left with. Now we want to write this as sigma ij ui comma j minus v sigma ij comma j ui dv. How can we do that? Let's look at this one, or integration by parts, whatever you like. Let me just put it over here. So sigma ij ui comma j, we want to apply a differentiation by chain rule. That will be sigma ij comma j ui plus sigma ij ui comma j. Okay, so sigma ij ui comma j sigma ij ui comma j is equal to sigma ij ui comma j minus sigma ij comma j ui. Okay, that's what has been done over here. Now this quantity can be written as, using the divergence theorem again, sigma ji nj ui ds minus sigma ij comma j ui dv. Okay, so this has been written as this using the divergence theorem. Now what you do is try to write 6.22, which is this one. Okay, and this one. So this quantity is clearly equal to 0. So this, if we forget, is this. So this quantity is clearly equal to 0, and sigma ij nj, okay, sigma ij nj is also equal to 0. Okay, so this quantity, sorry, this quantity is 0. Okay, let me just break this into two parts now. St sigma ij nj ui ds plus su, right, because s can be written as a summation, ij nj ui ds. We can write this as 0 because in ST this quantity is 0 and in SU this quantity is 0. Okay, because of this. Okay, so that's how we are writing that integral u 2 times of u dv is equal to 0. This implies, since 2 is not equal to 0 clearly, and it must be 0 for all arbitrary volumes, so this implies that actually u is equal to 0. Okay, this implies, remember u was half eij sigma ij, so this implies that eij is equal to 0 or sigma ij is equal to 0, and when I say this, all the terms. Okay, now the next so what does this mean, by the way? This means that eij1 equal to eij2, and this would mean that sigma ij of 1 minus equal to sigma ij of 2. Okay, so clearly the two things have been solved. Now if ui is equal to 0, on SU, okay, let me just say this. If the strain eij is equal to 0, this implies ui can at most be a rigid motion. See, since strain is made up of partial derivatives of this displacement, if the strain is 0, then it means that ui can at best be a rigid body motion. Okay, so there will be no spatial displacement. So ui of x will be constant. It won't be varying with x. Otherwise, it would start having a strain component. So if strain is equal to 0, then ui can at most be a rigid body motion. Now, if ui is equal to s0 on SU, this implies ui is equal to 0 everywhere, right? Because the same ui has to happen in rigid body motion. The boundary point and the point in the bulk will have the same ui. Okay, so this implies that ui of 1 is equal to ui of 2. So this means that you have shown that sigma ij of 1 is the same as sigma ij of 2. You have shown that eij of 1 is the same as eij2, and you have shown the ui of 1 is the same as ui of 2. This implies the problem solution is unique. Remember, we have proved it by contradiction. I mean, we started with two separate solutions and then we found that eventually they are the same. Okay. Now, few of the points which you should think about, what if this is not true? Okay, if ui is not equal to 0, then what happens? Okay, secondly, if the tractions are specified, if okay, tractions on ST are specified, okay, not on ST, on S, on the entire body, then ui of 1 and ui of 2 may differ by a rigid body motion. verify this, and in this case, can you still call the solution as unique? Only verify and then you will have an answer. Secondly, we have called the different solution as sigma ij, eij, ui. Okay. What is the meaning of this statement? I mean, what strain energy density is this? So what is the meaning of the strain energy density of this one, since sigma ij and eij is equal to the different solution? Okay. For example, if you elaborate this, you will have u is equal to half into sigma ij of 1 minus sigma ij of 2 eij of 1 minus eij of 2. Okay, that would mean half of sigma ij of 1 eij of 1 minus sigma ij of 1 eij of 2 minus sigma ij of 2 eij of 1 plus sigma ij of 1 sigma ij of 2 eij of 2. Okay, now the question is there any meaning of these terms? Think physically. Is there any meaning of the term sigma ij1 eij2 or sigma ij2 eij1? Okay, perhaps that's where you should have an answer to question like this. Okay, so these are some fascinating questions for you to come up with an answer, and it will be quite a good experience for you. Okay, now as I've said, this is the second reason why linear elasticity continues to be used so popularly. What does it mean? That if you find the solution to a elasticity boundary value problem, let me correct, if you find any solution to a formulated boundary value problem, you know for sure that that's the only solution to that problem. And this is a very powerful idea, that you have to find a solution using any method, and once you have a solution, you should be sure that this is the only solution. You do not have this privilege when the material is, say, plastic, when the material is viscoelastic or so on. That way you cannot claim uniqueness in this way. Okay, there are only very special cases in which you can do that, but not like this. So this is the second reason why linear elasticity is very popular and still continues to be used. So that is always the first thing you are taught. Okay, other than the principle of superposition. So I hope you can now see why we are learning this subject and why it is important for us to be able to understand and formulate the problem correctly. Okay. One of the other things which we must discuss is called the bounds on elastic constant. It is also telling us theoretically why the Young's modulus of a material has to be greater than 0, or the Poisson's ratio has to be greater than -1, and so on. Okay, so let's first take, just like in the earlier cases, we will conduct some simple tests. The first one can be a uniaxial tension. In this case, you have to write this as sigma ij is equal to, so for uniaxial, you know it will be this. Okay, and if you want to write, say, the strain energy density, one can write this as 1 plus nu by 2e into sigma square. I mean, we have just done that over here. Okay, sorry, this was this quantity 1 by nu by 2e sigma ij. So once you do that, you should be able to find for this particular case as nu by 2e sigma square, and this would be sigma square by 2e. Okay, now the strain energy density has been shown to be a non-zero quantity. Okay, it will be zero only when case there is no strain or no stress. That's a separate thing. Okay, so this quantity has to be greater than zero if there is any loading applied. In this case there is a loading, so we are not even considering the equality. Equality will hold when only there is no strain and no stress. Okay, so if this is greater than 0 and sigma square has to be greater than 0, 2 is definitely greater than 0, so this automatically implies that E is greater than 0. So the Young's modulus of any solid will be greater than 0. Do remember, we are making all these bounds on elastic constant using the isotropic Hooke's law. Okay, that's why you have only two constants over here. But eventually we will later show that it's valid for much more larger class of materials. Okay, so the Young's modulus is always greater than 0. Now consider a simple shear case. In this case, the state of stress at a point can be written as this. And again, the Hooke's law, so the strain energy density can be written as tau square by E and 1 plus nu. Now this quantity also has to be greater than 0 if there is loading applied, which it is applied, so it cannot be equal to 0. Now tau square will be greater than 0. E has been shown to be greater than 0. Now the only possibility is that 1 plus nu has to be greater than 0 or nu has to be greater than minus 1. So this tells us that the Poisson's ratio of a solid has to be greater than minus 1. So these are theoretical bounds on a solid. You cannot have a solid which follows the properties which you are using and can have a nu which is say less than minus 1. So that cannot happen. Now let's see another case, which is a hydrostatic compression. In this case, as you know, you would write, so since it's a compression, you will have a minus sign. Just to help you, I mean, most of the geotechnical engineers, rock mechanicians, they use compression as a positive because all the rocks are naturally under compression, so they don't put compression under negative. We in mechanical, aerospace, and the general industries use compression as negative, but we'll follow with our system, though it doesn't really change anything. The sign convention doesn't really change anything. Okay, so sigma ij is equal to minus p 0, 0 minus p 0, and 0, 0 minus p. And in this case, again, the uh, strain energy density comes out to be, for a linear elastic isotropic solid, of course, by 2e minus 3p square, and this comes out to be 3p square by 2e 1 minus 2 nu. Now this has to be greater than 0 because it's a strain energy density. P square is definitely greater than 0 since it's a square. 3 by 2 will definitely be greater than 0. E has been shown to be greater than 0, and the other possibility, the only possibility is that happens, and this means that nu has to be less than 0.5 or 1 by 2. Okay, so it definitely places a bound on your elastic solid. This has to be less than half and greater than minus 1, combining the last two properties. So you will not find a Poisson's ratio of a solid which is less than point half or point minus 1 or greater than half. It has to lie within this range. Okay, so you can also combine the, again, all this is valid for linear, elastic, isotropic solid. We know that because we are using the strain energy density function for a isotropic solid. There are complications when you have anisotropic or some other types of material, but let's just stick to what we know. So if you follow the table which was given between the constants k, nu, lambda, mu, and so on, you can also derive that k will be greater than 0 and mu will be greater than 0 using the properties which you already have, like E, and you have a bound for E which is greater than 0, you have a bound for nu which is between -1 and half, not including the endpoints. Okay, so this is where we have learnt about the bounds on the elastic constants, linear elasticity constants, for obviously an isotropic material, since that is our domain. So okay. Okay, the next topic which we would want to learn is the principle of virtual work, and this is a subject which is perhaps the starting point of a more elaborate course on FEM. We won't be discussing FEM, but we will be discussing the principle which guides the use of FEM in elasticity problems. So let's define a few terms before we can tell what the principle of virtual work is. Okay. So we have something called a virtual displacement. Of a point in a continuum solid is the fictitious displacement such that the forces acting on the point remain unchanged. Definitions are very important over here, so please understand this. Okay, so virtual displacement of a point in a continuum solid is the fictitious displacement, meaning it is not real, such that the forces acting on the point remain unchanged. So if this is the point of interest, whatever be the real forces acting on this point, okay, that remains unchanged, and now this should have a virtual displacement, and that value is called as a virtual displacement of this material point. Okay, now we have another definition. The work done these forces during virtual displacement is called the virtual work. Okay, so to define the principle of virtual work, we'll have to first tell what the virtual work is. So this is a work done by these forces, the forces which remain unchanged during this virtual displacement. Okay, now if there is an object which is in static equilibrium, that would automatically mean that the virtual work for that is 0, since all portions of that solid will have a 0 uh, resultant force. Okay, so for this, say the same point which was of interest, the work will be 0 over here on this particular point, not because the virtual displacement is 0, but virtual work will be 0 because if resultant forces on this point are 0. Okay, so that's why you have virtual work as 0 for a body which is in static equilibrium. For a body which is static equilibrium means small parts of it which can be shrunk to a point are also in equilibrium. And the converse is also true. If the virtual work is 0, then the material point must be in equilibrium. Okay. Now let's first now get into the symbols and before we get into the maths of it. So the virtual displacement for any point can be written by this symbol, this del symbol, and it will have three components: virtual displacement in the x direction, virtual displacement in the y direction, and virtual displacement in the z direction. Okay. Consequently, you will also have the virtual strain, which will be defined just like a real strain was. You will take the partial derivative of the virtual displacements. Okay, so this is the notation we will use. Okay, now if you take up a elasticity boundary value problem, okay, and you know that there will be a part of the boundary ST which will have traction specified, and then you have part which has the displacement specified. Okay, so this is something which we know. Now we have to imagine, these words are important. Imagine that the body undergoes delta ui, okay, from its equilibrium configuration. So the body undergoes a virtual displacement means, I mean obviously this virtual displacement was a function of this material point. So wherever, so this is the origin, say this point is lying at this position vector, it is imagined to undergo a virtual displacement delta ui from its equilibrium configuration. It's not actually going, but we are imagining that this virtual displacement is happening. Okay, now this virtual displacement is arbitrary except that it must not violate the kinematic displacement boundary condition. So if the displacement, the real displacement, okay, you see how I differentiate between a virtual displacement and a real displacement. If ui is equal to 0 on SU, okay, this would mean that delta ui will be equal to 0 on SU. So inside the bulk, the virtual displacement can have arbitrary value, okay, which is delta ui, but it must not validate the kinematic displacement boundary condition. Okay, so by this it's not violating. So the virtual displacement is arbitrary as long as it satisfies this. The reason this is done is that we don't want the boundary conditions to change. Okay, that's why we are ensuring that the original boundary value problem does not actually change. In our quest to find an answer, we should not actually change the boundary conditions. Okay, Now the virtual work done by the surface and the body forces, let's see. The work done, let's write, by the surface forces would be the surface force density, which is this, into delta ui. And then similarly the body force density Fi multiplied by dV will give you the force, and delta ui gives you the displacement. So you may be aware that the real work is integral of F dot du. Okay, now this becomes equal to, if you take a dot product, this becomes equal to F I dui. Okay, and the virtual displacement can be written similarly as delta u by d, delta ui. Okay, so this is how we have written. So this is the virtual work done by the surface and the body forces. Remember, in this expression, what is virtual? W is virtual, this displacement is virtual, but the forces and the tractions on the boundary are real. That's why they don't have this delta symbol in front of them. Okay, now let me say, what we want to do is we want to say the following. Let's first write this as delta W is equal to ST Ti delta Ui ds plus V Fi delta Ui dV. Okay, now if this could be written as S Ti delta Ui ds minus, hold on. So what we want to say is that we want to write it as S Ti n delta Ui ds plus V Fi delta Ui dV. So look at how that works. So Tin delta Ui ds is equal to St Tin delta Ui ds plus Su Tin delta Ui ds. Now on Su, the Tin is equal to 0. Okay, sorry, I'm sorry. On Su, the delta Ui is actually equal to 0. Okay, because of this kinematic boundary condition, and hence we can write that St Tin delta Ui ds is equal to S Tin delta Ui ds. So that's the reason we can write this. Now you want to use the relationship between traction and stress. Tin, if you remember, was sigma ij nj delta Ui ds plus V Fi delta Ui dV. Okay, and this can be written as you want to now use the divergence theorem to convert this surface integral to a volume integral. Okay, so we have done this several times in this course, so by this time you should know how I am applying this. Fi delta Ui dV. Okay, so this is something I will write for you to verify how can this be written using the divergence theorem? It's important, please don't ignore this. Now you apply the chain rule of differentiation. So that would be sigma ij comma j delta ui plus sigma ij delta ui comma j dv plus fi delta ui dv. Just to correct that, we are writing a delta w, which is the virtual work. Now sigma ij comma j plus fi is equal to 0 according to the equilibrium equation. So this can be written as minus fi delta ui dv plus sigma ij delta ui comma j dv plus vfi delta ui dv. So the first and the last step cancel, and we should get first and the last value cancels. This cancels with this. So this can be written as v sigma ij delta eij dv. Okay. So this is the virtual work which we have. This is also called, or can be written, this last term, as the virtual strain energy density, or not density because we have multiplied by dV. So this value is sigma ij delta eij dV, and if you expand it, we should have a sigma x delta ex plus sigma y delta ey plus sigma z delta ez plus tau xy delta gamma xy plus tau yz delta gamma yz plus tau zx delta yzx dv. Okay. Now this is the virtual strain energy, which was, we derived it as delta W, but we have written as a virtual strain energy because of the work energy equivalence. Okay. Now if you compare this with the actual strain energy, okay, you will see that a factor of half was missing. Okay, if you remember, U was equal to half sigma ij eij in the real strain energy density, and the virtual strain energy density is actually sigma ij delta eij. Obviously it's virtual because delta eij is the virtual strain. So there's a factor of half which was there and it's not over here. The reason for that is because in the real strain energy density, the stress was increasing with strain, okay, and linearly, so it was like this. On the other hand, let me show this. Yes, okay. On the other hand, in the virtual setup, the stress remains constant, okay, because the force remains constant. You remember that's the definition of a virtual displacement. In a continuum solid, is a fictitious displacement such that the forces acting on the point remain unchanged. Since the forces acting on the point remain unchanged, the stress also remains unchanged, and that's how you get this behavior. So in one case, the area under the curve will be this entire triangle. In the other case, it is just half of it. That's why you have a factor of half in this case. Okay, so that explains why The factor of half is missing in terms of the virtual strain energy. Now there is an assumption which has to be made, that the strain energy can be expressed in terms of strains. So we have seen that sigma ij is equal to dou u e. Again, I am writing with a vector sign because I want to write a bold symbol, but since I don't have a way, I am writing it like that. So this is something which we have seen before. Mind you, this is all the real strain energy and the real stresses and real strains. Okay, this is something which we knew. Now what we want to do is we want to substitute this over here. Okay, so what we want to write is that sigma ij delta eij dv is equal to, we want to write sigma ij as dou u. I'm not writing as a function of strains because it's implicit now. Now we can write it as delta into dou u and this quantity can be written as u dv. Okay, this is the so-called total derivative. If you are not sure, please check what a total derivative is. Okay, and this, if you remember, was delta w. Okay, the logic we could do this step was this step. The external forces are unchanged during virtual displacement and the region So we are calling this delta as an operator, okay, and it has this property that it can be taken out, say from here to here, because of the fact that the external forces will remain unchanged during this virtual displacement, and the region V is fixed, so that nothing happens to this small region dV. the operator delta can now be placed outside. Okay, so that was the reason. Fine. Now you want to write a delta u, sorry, u dv, okay, minus delta w is equal to 0, okay, by taking this and this. And if you recall that delta w could be written as this over st and the volume, so both the surface tractions and the volume. So we'll write the delta w as that. So I'll take this, sorry, this should not be there, okay. I'll take this delta as an operator outside, write it as u dv minus and this is delta into ut minus w is equal to 0. So this is a statement of the principle of virtual work. The quantity ut minus w is the total potential energy of the elastic solid. So what does this relation state? It states with the change in potential energy during a virtual displacement from equilibrium is 0. This is the statement of the principle of virtual work, that the change in potential energy during a virtual displacement from equilibrium is 0. Okay. One of the statements is that this, one of the facts is that this is valid for linear and non-linear elastic solid. Let's see that why. See from the start. Okay. So the definitions of displacement are there. The definitions of small strain are definitely made when you write this. Okay. Now this is the boundary condition, so it has got nothing to do with linear or non-linear solid. This is the work done, which has got nothing to do with linear or non-linear solid. Okay. To be able to write this STS-SU also does not require any distinction between linear and non-linear elastic solid, because delta ui would be 0 on SU anyways. The relationship again between the traction and stress is independent whether the material is linear elastic or not. Okay. See, we did not invoke the Hooke's law anywhere. Now again, using the divergence theorem also is okay for all types of elastic or non-linear elastic material. The equilibrium equation which is used in this step, okay, is also independent of the fact that the material is linearly elastic or not. Okay, now come to this part. Obviously we are referring to this case, and hence this is not what we are referring to. Of course this was there for comparison, but for right now we are referring to this. Now the strain energy can be expressed in terms of strain. This expression, if you recall, even though we had derived it for linear elastic isotropic solid, I had claimed that it is valid for non-linear elastic materials, even hyperelastic materials as well, and hence its substitution over here, okay, is also valid for both elastic and non-linear elastic and non-linear elastic materials, and the rest of it is also, there's nothing new about it. So that is why we are saying that this principle is valid for linear and non-linear elastic solids. So what we want to now do is re-derive the basic equilibrium equations and boundary conditions for a elasticity problem. Okay, so let's start with the relation which we had before. Okay, let's start with here what we have. Where did it go? Somewhere over here. Okay, so this is what we have derived. Not what we want to do is we want to start from this point and then go back and see whether we can get the equilibrium equations. So that would mean that the theorem of principal virtual the principle of virtual works both ways. Okay, so the change in potential energy during a virtual displacement from equilibrium 0, and the other way is if it is in equilibrium then the change would be 0. So either ways we can do it. So let's start now from over here and then we'll try to go back to where we started. Okay, so I'll just put it over here. Okay, so we have V sigma ij delta Eij dV minus S di n delta ui ds minus fi delta ui dv is equal to 0. Okay. Now if you look at this particular term, the first one, we should be able to write it. Let's write these separately. That's sigma ij delta Eij. I can write it as sigma ij, then delta Eij will be delta ui comma j plus delta uj comma I. Obviously there's a factor of half over there, and this can be written as sigma ij delta ui comma j. First of all, how can this be written? Quite easy. See this expression, write it as half sigma ij delta ui comma j plus half sigma ij delta uj comma I. This can be written as half into sigma ij delta ui comma j plus half into sigma ji delta uj comma I. This can be written because stress is symmetric. Okay. Now this can be written as half sigma ij delta ui comma j plus half. In this expression I can interchange I and j because both of them go from 1 to 3. so that would not make any difference. So I will interchange I and j and write it as okay. So that explains why we have written it like this. Now this is also written as equal to sigma ij delta ui comma j minus sigma okay. Now that also should be easy, it's just the chain rule of differentiation. So sigma ij delta ui comma j is equal to sigma ij comma j delta ui plus delta ui comma j sigma ij. Okay, so this is this one and you can easily write it. So now I want to uh, substitute this green part into the first term over here. So I can write sigma ij comma sigma ij delta ui comma j minus sigma ij comma j delta ui dv minus the same remainder expressions. Okay, let's see. Can write it as sigma ij comma j plus fi delta ui dv plus s din delta ui din minus sigma ij nj delta ui ds equal to 0. Okay, so one of these terms has yes, so what has been done is this term has been taken with this term, okay, and this term has been taken after applying the divergence theorem on this term. So this volume integral has been converted to the surface integral, okay, and that's what has happened over here. So this with this, so this is this and this is this one. So this is something which you should verify. Okay, now for any arbitrary delta ui, this relation is satisfied if, let me write the above relation, each of the two terms are 0. So that would mean that sigma ij plus fi is equal to 0, and either delta ui is equal to 0 on SU, or Ti of n is equal to sigma ij nj on St. Okay, so because delta ui is arbitrary, so the only possibility that this will always be 0 if when these two integrands are 0. So the first one is definitely 0. Okay, and there are two more conditions. This s you can write as either tin minus sigma ij nj delta ui ds is equal to st tin minus sigma ij nj delta ui ds plus su tin minus sigma ij nj delta ui is ds. Now when we say that either delta ui is equal to 0 on su, that means that this particular thing is 0. Okay, and if this particular thing is 0, then and the other possibility is that on st this particular term is equal to 0. Okay, so this is equal to 0. So in either of these two cases you are able to get this. So you can see that we have re-derived the equilibrium equation by starting from the principle of virtual work and along with the boundary conditions. So SU, if you have to call them, you would call it as essential boundary conditions, and ST are the so-called natural boundary conditions. So what we have demonstrated is that the principle of virtual work can be used to generate equilibrium equations and the associated boundary conditions for a elasticity problem. In the first part of this discussion, we did the reverse. We assumed that equilibrium was valid and the boundary conditions were holding, and then we arrived at the principle of virtual work. So as you can see, you can move either from equilibrium to principle of virtual work, or the principle of virtual work to equilibrium equation. So we have demonstrated both. Okay, now let's see a principle of minimum potential complementary energy. So what we want to do is we will be defining these two principles, which are, as I have said, is one of the important methods to numerically solve the elasticity boundary value problems. FEM is the most popular method which is used over here. We won't be using it, but we are just defining the principle, these principles. Okay, so the potential energy pi is written as ut minus w. So we don't call it the minimum potential energy anymore, we'll just call it the potential energy. Okay, so what did this statement show? We have already shown that the virtual work statement indicated that the variation in potential energy from an equivalent configuration was 0. So to understand this word variation, I mean, there is also a principle of variation in mathematics, and I'll simply explain what this is. So suppose there are 2 points and you want to draw the curves which join these two lines. Okay, so you can have a curve like this, you can have a curve like this, okay, or you can just have a curve like this. Okay, now if I tell you that the minimum distance is actually for this black curve between these 2 points, and I will then state that any variation, even a slight variation from this path, will only make the distance between these 2 points longer. Okay, can you see that? Red and green are the other examples. These orange are somewhat slight variations from this distance. So this is where you can see that any variation from this particular straight line, the earlier black line, okay, will cause a change in the distance between these 2 points. So you will say that the variation in distance from the 2 points will be 0 if you want to have a minimum distance. So similarly, you have just written that the variation in potential energy from equilibrium, for our case, this black line, this black straight line was the equilibrium distance, okay, is 0. Okay, so we have that over there. The other sort of more fancy way of saying is that the potential energy, we don't, as I've said, don't call it the minimum potential energy anymore, we just call it the potential energy. The potential energy is stationary in an equilibrium configuration. If the variation is 0, then we say that it's a stationary or a stationary point. So it will take a local extremum that can be either maxima or minima. So in literature, it has been shown that it is actually a local minimum. This proof that it is actually a local minima and not a local maxima is outside the scope of this particular course. Okay, but you can find out the literature, it's very standard. Your textbook also has those references. Okay, so let's state principle of minimum potential energy. Of all the displacements satisfying the given boundary conditions of an elastic solid, those that satisfy the equilibrium of all the displacements satisfying the given boundary conditions of an elastic solid, those that satisfy the equilibrium equations make the potential energy a local minimum. Okay, And since the potential energy is a local minimum, it's an equilibrium. So it's the same stated principle which we have. Now we can also, I mean, this is the same principle which we have above, just a more fancy way of writing. So out of all possible displacement satisfying the given conditions, you will only choose the ones which are making the potential energy as a local minima, which is a stationary point, and because that will be sure that it is actually making the solid in equilibrium, or that point in equilibrium. Okay. So we want to now reverse the nature of variation. Until now we had been varying the displacement. Okay. Until now we were taking delta ui. Now we'll take a reverse of this. Okay. Holding the displacement constant, let in the earlier case the forces were held constant while the displacements were varied. In this case the reverse will happen. So here the displacements will be constant and the forces or the stresses will be varied. So let's see. Let sigma ij be the actual stresses that satisfy equilibrium equations and boundary conditions. Now consider a system of stress variations or virtual stresses that will be shown by delta sigma ij. Now if you have the stresses which are varying with for a cold constant displacement, the equilibrium conditions with so the body forces will also now be, eventually the point is that the forces are varying. So body forces, tractions, stresses, all of them should be varying. So now we want to define a quantity called the virtual complementary virtual work. Complementary virtual work. This will be ui delta ti n ds. Please compare this with the earlier case. If you apply the same steps of reduction which we had done earlier for the virtual work, for the complementary work also, you will be able to write Okay, this is something for you to verify. That following the same steps, you should be able to do this. Please don't ignore this. That will be a check whether you have understood the previous things or not. Okay, and this quantity, just like the last time, is called the complementary virtual strain energy. Again, we will be using this. Okay, UC is this strain energy, complementary strain energy density. Okay, so this is the complementary strain energy density, and you will substitute this again over here and follow a similar method as we had last time. So that should eventually give you a delta of UTC minus WC is equal to 0. This shows that the variation in the total complementary energy, okay, so pi c can be written as UTC minus WC, is 0 in an equilibrium configuration. Okay, so this is just a corresponding principle. So we should write the principle of minimum complementary energy. So this only states that it will be an extremum, but again it is a local minima because of certain literature from before which are outside the scope of this course. Now, what is the definition of this? Of all the elastic stress states satisfying the given boundary conditions, those that satisfy the equilibrium make the complementary energy a local minimum. Here the variation is obviously in the stress states or the forces at a more fundamental level. So if you have, say, a linear elastic solid and you have one-dimensional state of stress, so this will increase like this. One small element, something like this, is du is equal to sigma delta E, okay, and something like this is duc is equal to E delta sigma. This is u, this is uc, and u will be equal to uc in this case because it's a linear material, linear elastic material. However, in the other case, if it's a non-linear, elastic solid, then u is not equal to uc. So the area under the curve and above the curve will be different. Okay. So that is the end of our principle of virtual work. There is an example about an Euler-Bernoulli beam theory which you should be reading. So study Euler-Bernoulli. To be able to study this, you will have to revise your concepts which you should have learned in your second year undergraduate course in solid mechanics about beam bending. So please do that and then see how this principle is applied to solve the same problem. Okay, this is a part which is of self-study, and the example is given in the book. The last subtopic in this strain energy is again a very simple situation of so-called Rayleigh-Ritz method. It's one of the methods to solve this problem using the principle of minimum potential energy. So let's just see what that method is. The eventual objective is always to find the displacement, strains and stresses inside the bulk of a solid. Okay, so in this particular method, what we do is we construct a series to U2 U naught plus J equal to 1 N AJUJ. So this is a trial approximation, and similarly you will have V equal to V naught plus BJ VJ, and W is equal to W naught plus CJ WJ. Now the functions, now these are not scalars, these are all functions. Okay, they'll be functions of space. U naught, V naught, W naught are chosen to satisfy any non-homogeneous displacement boundary condition and Uj, Vj, Wj satisfy the homogeneous boundary conditions. Anything which is non-zero essentially. Okay. So they can be, for example, some sort of a polynomial or a trigonometric function, very depending on what the problem is. So this trial functions anywhere and everywhere always comes by experience. So you can't like randomly choose a function. You will have to do some experience with the problems and solving of a certain kind, and then this trial solution begins to work. Okay. Now the objective is to obviously find the coefficients, which is Aj, Bj and Cj. Okay, because if you have the coefficients, you will have the displacements, and once you have the displacements, you can find the strains or whatever else you would want to find. So the Aj, Bj and Cj are unknowns. So the total potential energy has to be formulated in such a way that it's a function of Aj, Bj and Cj, and since it has to be minimum for a variation in Aj, it should be delta pi by delta Aj equal to 0. It should also be a minimum with respect to Bj, and it should also be a minimum with respect to Cj. Okay. Suppose 3 have to be satisfied, and it's a 3n. So n is basically depending on how many terms you are taken. 3n equations, algebraic. It will be algebraic because as soon as you partially differentiate it with respect to this, you will just have linear equations. Okay. So assuming you will be able to solve this system using either of the methods, Gauss elimination method, pivot point and things like that, you should be able to find what these all unknowns are. Once you have all these unknowns, you have the displacement at any point in the elastic solid. So there is again an example of an Euler-Bernoulli beam, which you have to self-study and read. I'm leaving out for self-study because it requires you to go back and revise your earlier chapters, earlier parts of mechanics of solid, strength of materials, whatever you used to call it. Okay, by Rayleigh Ritz. But you should do this and then compare how is this method compared to your earlier understanding of solid mechanics. How does it improve our earlier understanding of mechanics of solid, this knowledge of elasticity? Okay, so in the next discussion, we'll be discussing about the two-dimensional approximations of plane strain and plane stress. Thank you.